At first glance, the idea of sitting in a moving vehicle, say a train picking up speed, doesn't seem like it should alter your sense of space or time in any fundamental way. You might feel a jolt, maybe lean back a bit, but everything around you still looks mostly normal. But in physics, especially in Einstein's theory of relativity, acceleration is not just a matter of feeling pushed. It's a transformation of reality itself, and the deeper you explore what it means to observe the universe from an accelerated frame, the more you uncover a strange and beautiful paradox. Space and time begin to warp, bend, and shift in ways that challenge our most basic intuitions. This is the heart of the accelerated frame perception paradox. Imagine this: you're not just accelerating in a car, but in a spaceship. There's no window to the outside, and no gravity to keep your feet on the floor. Except for one strange fact: as your spaceship accelerates, you begin to feel a force pushing you down, mimicking gravity. According to Einstein's equivalence principle, there's no local experiment you could do to distinguish between being at rest in a gravitational field and being in a uniformly accelerating frame. In other words, acceleration and gravity are indistinguishable. But that's just the beginning. Observers in accelerated frames begin to perceive time and space differently from those at rest. One striking effect is time dilation, already familiar from special relativity, but in an accelerated frame, the situation becomes more dramatic. The clock closer to the direction of acceleration ticks slower than a clock farther away. In a spaceship accelerating at 1 g, if you place two clocks, one at the floor, one at the ceiling, they would measure time at different rates, as if the spaceship were sitting on a planet with gravitational curvature. And then there's Rindler space.a, a way of describing space-time from the viewpoint of a constantly accelerating observer. In Rindler coordinates, the universe seems to end at a boundary called the Rindler horizon. Anything beyond this horizon cannot be seen or influenced, no matter how long you wait. To someone accelerating hard enough, even part of flat, empty Minkowski spacetime looks like it contains a horizon, similar to that of a black hole. How is this possible? Because light from certain regions simply can't catch up with the accelerating observer. The faster you accelerate, the more of the universe slips beyond your horizon. This suggests that acceleration shapes your visible universe, limiting what you can perceive, even in completely flat space. You might ask, do observers in different frames see the same events happening in different orders? Yes, and this is where the paradox deepens. In non-accelerated, inertial frames, simultaneity is already relative. Two events that are simultaneous for one observer may not be for another, but for accelerated observers, the definition of now bends even more. Depending on your acceleration, your concept of time can tilt and twist, so events that seemed neatly ordered to one person may become causally ambiguous or even reversed for another. And it gets stranger still. If an observer accelerates long enough, physics predicts they might experience something called the Unruh effect. They will detect a warm glow of particles in what an inertial observer would consider a perfect vacuum. Essentially, the accelerating observer perceives the vacuum as a thermal bath, a bizarre quantum effect that's still being debated and explored. To you, as the accelerated traveler, it would feel as if empty space is not truly empty, but filled with warmth and radiation that someone at rest would swear isn't there. So why is this a paradox? Because it shows that what we call reality is deeply dependent on our motion, not just in terms of how fast we're going, but in whether we are accelerating. Observers in different frames don't just disagree on speed or position, they may see completely different horizons, temperatures, even particles. The very fabric of space and time, what is here, what is now, becomes subjective, shaped by motion in ways that defy classical logic. In everyday life, we don't notice this. Our accelerations are too small, our reference frames too similar. But in the extremes, near black holes, in high-energy particle accelerators, or aboard relativistic spacecraft, these effects matter. They don't just shift your perspective, they reshape the universe as you experience it. And perhaps that's the most profound insight of the accelerated frame perception paradox, that space and time aren't fixed backgrounds but dynamic, observer-dependent quantities. They stretch, curve, and dissolve depending on how you move through them. The more you accelerate, the more the universe reveals just how deeply intertwined motion and perception really are. In the end, acceleration doesn't just push you forward, it pulls open new layers of reality, revealing that what we see is always filtered through the path we take. The accelerated frame perception paradox refers to the counterintuitive ways in which observers in non-inertial, accelerating frames of reference experience space and time, unlike inertial observers who perceive space and time according to special relativity. Accelerated observers witness bizarre distortions, including time dilation, horizon formation, and anisotropic space curvature. These perceptions break with everyday experience, where space and time appear uniform, absolute, and shared by all observers. The paradox reveals that acceleration warps reality in a way that challenges Newtonian intuition and even extends the implications of Einstein's theories. An astronaut in a rocket experiencing constant acceleration feels a gravitational field indistinguishable from Earth's gravity, despite being in deep space. It's like sitting in a fast elevator that never stops. You feel pulled down, but the sensation is created not by a planet, but by acceleration alone. In special relativity inertial frames, those moving at constant velocity share symmetrical laws of physics. However, accelerated frames require general relativistic corrections. Observers in such frames experience non-uniform time flow, perceive spatial curvature, and may even detect horizons where events become unreachable. Acceleration introduces asymmetry. Clocks tick differently, rulers appear distorted, and simultaneity breaks down across the frame. The observer's reference system becomes locally Lorentzian but globally curved, redefining what they perceive as real. A clock held in the rear of an accelerating spaceship ticks faster than one at the front due to the difference in acceleration-induced gravitational potential. It's like being in a train where the floor is tilting. Time flows faster at the lower end, even though the whole system is moving forward. The mechanisms behind these paradoxes lie in the equivalence principle, which states that acceleration and gravity are locally indistinguishable. In an accelerating frame, space-time is warped. Clocks run at different rates depending on their position relative to the direction of acceleration, and objects appear compressed or stretched depending on the acceleration vector. These effects arise from Rindler coordinates, the mathematical framework used to describe uniformly accelerated observers in flat spacetime. Rindler horizons form behind an accelerating observer regions of space that permanently recede beyond the observer's reach, mimicking black hole event horizons. It's like running uphill while the ground behind you collapses into darkness. You can never go back, and the faster you go, the more the past disappears from view. Accelerated frame perception is a rich topic in complexity science and theoretical physics, illustrating how local measurements can mislead about global structure. Complex systems often evolve in non-inertial curved spaces, such as expanding universes or rotating fluids, where perceptions depend on relative motion. Observational relativity becomes critical. What is now for one observer may be a distant past or unreachable future for another. This leads to emergent causal asymmetries, new types of horizons, and frame-dependent physical laws. In rotating frames, like those near a Kerr black hole, time loops, closed time-like curves, can theoretically exist. Causal paradoxes that arise only for observers in these frames, it's like watching a movie where your seat changes the plot. Each position in the theater shows a different sequence of events. One of the most striking implications of accelerated frames is the Unruh effect. An observer accelerating through vacuum perceives a warm bath of particles, while an inertial observer sees empty space. This arises because the vacuum state is observer-dependent. What one sees as zero energy, another may interpret as thermal radiation. Accelerated observers thus interact differently with quantum fields, implying that energy and particle content are relative to motion. A particle detector in uniform acceleration registers a thermal spectrum of particles, suggesting that vacuum is not absolute. It's like entering a cold room at high speed and suddenly feeling heat all around, not because the room changed, but because your motion stirred up its hidden contents. Accelerated frames challenge the notion of a shared objective reality. They demonstrate that information is not globally invariant, but frame-dependent. What one observer can detect and measure may be inaccessible to another. In information theoretic terms, acceleration redefines causal connectivity, entropy flow, and observable domains. This leads to limitations on data synchronization, signaling, and perception of order, with deep implications for both classical and quantum systems. In relativistic quantum information theory, entangled particles observed by accelerated detectors appear decohered, as if the entanglement were lost, due to Rindler horizon effects. It's like two musicians trying to play a duet, but one is on a ship accelerating away. What sounded harmonious becomes discordant due to time shift and communication lag. The study of accelerated frames is critical for understanding cosmic inflation, gravitational waves, and artificial intelligence in relativistic environments. In cosmology, observers in different regions of spacetime may experience different vacuum states or histories. In gravitational wave detectors, acceleration corrections are essential for accurate measurements. In AI systems deployed in orbit or high-speed platforms, accounting for frame-dependent timing will be crucial for coordination and data integrity. So, GPS satellites must correct for both gravitational and velocity-based time dilation to remain synchronized with Earth-based systems, a practical manifestation of relativistic acceleration effects. It's like trying to keep a group chat in sync when each participant is moving through time at a different rate. The app crashes unless the clocks are corrected. Visualizing accelerated frame dynamics is inherently difficult, as our cognitive intuitions are built around inertial experiences. Diagrams and equations that describe time dilation, curvature, and Rindler horizons often conflict with common sense. Measuring frame-dependent effects requires precise synchronization, extreme conditions, and careful control of reference frames, which is non-trivial in both experimental and computational contexts. Detecting Unruh radiation in a lab remains an open experimental challenge because the required accelerations are extremely high. It's like trying to see wind with your eyes. It's not the wind, but its effects on particles that make it visible. Understanding perception in accelerated frames is not just a theoretical exercise. It holds keys to quantum gravity, space-time engineering, and relativistic computing. Future work may involve creating artificial observers, e.g., sensors on accelerating platforms or quantum probes, to map time flow and event structure in new regimes. As human technology moves into relativistic contexts, space travel, black hole imaging, or quantum satellites, this knowledge becomes essential for designing systems that can operate under altered perceptions of reality. Next-generation missions, near black holes, or in highly accelerated interstellar probes will need to account for onboard and remote perception discrepancies to navigate and communicate reliably. It's like building a telescope that not only bends light but also bends time. You must recalibrate your notion of now to match what the universe actually reveals.